All right, we started 9.2 last time, series and convergence, and we had ended with talking about some theorems about, or properties of infinite series, and we were going to do an example. So that's actually where we're going to pick up, is with an example of that. All right, so we're going to determine the convergence or divergence. Of the series. Okay, and the example that we're going to look at is the sum from k equals 0 to infinity of 1 over 2 to the k minus 1 over 3 to the k. I guess in all technicality this is in parentheses, so I'll do that too, make it clean. All right, so one of the properties of limits above, our properties of infinite series, which includes our limits, is that if we have a sum of two sequences, which is exactly what we have, we can actually separate it, if they both indeed have a limit, into the sum of their limits. So we're going to be able to rewrite this as two individual sums. All right, cool. So I know you haven't actually maybe done the homework for this lesson, which is totally cool because you didn't have to. But do you remember from our discussion last time what kind of series these are?
Geometric.
They're geometric. Very good. So remember, geometric series have the property that you multiply by the same value repeatedly to get the subsequent terms. So for example, let's just take a look at that first one. Since we have been a little while, if I put k equals 0, and this would be 2 to the 0. And then I would have 1 over 2 to the 1, and then I'd have 1 over 2 to the 2. And what would be my common ratio that I would be multiplying by every time in this particular example? 1/2, yeah. So it is geometric. Obviously, geometric series have this sort of exponential form to them. Okay, so the beauty is they are geometric. And the lovely thing about geometric series is that you not only can know if they converge or diverge, but if they converge, you can also find their limit, right? Absolutely. So what about these two? Do they converge? Do they diverge? Do I have one of each? What's going on with these particular series? They do. They both converge. How do you know? You guys are like sort of under your breath trying to say things, just in case you're wrong, I can tell. What was that?
It's 2 minus 3 over 2, but that's just...
Okay, we'll get to the sum in just a second, but before that, we have to establish it really works. Shayna? No? Okay. The ratios are less than 1. So, Kristen, right? Okay. Kristen, what's the ratio for the first one? We already said that one, but what was that? Do you know what the ratio was for the first one? 1/2, yeah. The ratio is 1/2, and then we didn't actually do this one, but I think you guys can figure it out pretty quickly. 1/3. So these ratios are actually between 0 and 1. That's what makes them converge. Everybody good with that?
Is that the, okay, so it's a geometric is AR to the n, correct?
Yes.
Is your A just 1?
It is on this one. The A is just 1. The other thing that you can think about when you're saying it's AR to the n is A would be your first term. So it's whatever you get when you plug in n equal to 0. Do you see that? On this one it would be 1.
Okay.
You good? Yeah, A is your first term. Okay, so as Ethan mentioned, this actually means that we have a, okay, I'm running out of space. Let me do this. Okay, just like that, I have more space. Isn't that beautiful? You know, when you try to do that on paper, it doesn't work very well. Trust me, I've tried. Okay, so this actually has the form, we had said, of A over 1 minus R. Each of them individually does, right? So you had mentioned, Kyle, that the first term then in the sequence must appear to be 1, right? And you're right, it is. So for the first one, we have 1 over 1 minus, what's R? We said 1/2. And on the other one, we have 1, again, as our leading term, and then it's 1 minus 1/3.
Would it be minus instead of plus?
Oh, no, it's minus. It's minus.
No.
Oh, I see what you're saying. I'm sorry. You're right. This should have been subtraction. My bad. Thank you for fixing that for me. Okay. Very good. Simplify your fractions. I'm a fan of getting rid of fractions inside of fractions, kind of as my first step of business. So this is 2 over 2 minus 1, minus 3 over 3 minus 1, leaving me here with 2 minus 3 halves. What is 2 minus 3 halves? 1/2. And because this is actually what it asked me to do, it converges. And it converges to the value 1/2. Cool? Almost just like an extension of what we already knew about geometric series, or a combination of that with this previous theorem on this page.
I have a question.
Yes, ma'am.
So, in the summation, when do we have to make sure that k equals 1 instead of k equals 0?
Geometric series establish that the k equal, or that the index at the bottom starts at 0 in order to use that formula. So if it started anywhere else, if this k started at 2 or 1, then this expression would not actually give you the sum. You'd have to make amends. You'd have to fix that in order for it to happen, to make it work.
Like not yesterday, Wednesday, did we have to change one?
We did. We changed one and we readjusted it.
Okay.
And
We
kind of...
changed it to 0.
We did. We changed it to 0, and this kind of stems back to Kyle's question when he was looking at this and saying, so is the A value 1? And the answer is yes. And one of the things that I had mentioned was the A value can also be thought of as the first term you would get if you were to plug this into the sequence. I mean, if you try to figure out what the sequence looks like before you put the summation to it, then your first value is also what A is. So on this one over here, we'll go to the one that you're talking about. Did I skip it? There it is. I did. On this one over here, when we were looking at this particular version of it and trying to figure out what we do to get that to say n equal to 0, starting at n equals 0 instead, if you take a look at what happens when you plug in the number 1, or at the first term we wrote up here, that value is 36 over 100. That is A.
Okay.
It is the first value in the sequence. And so if I use that value, then I have reset it to n equals 0.
Okay.
So if you just figure out what the first value is, you can do the reset on the expression right away. Yep. Okay, one more thing in this section. This is a very, very nice fact, but it's often confused. It's often confused for its contrapositive. So let me just show you what I mean. All right, so let's start with, this is theorem 9.8. And this is the limit of the nth term. Okay, so this is a fact. It is always true that if we have a converging series, n equal 1 to infinity, n equal anything, 1's not special. I mean, it really isn't. We're just using it, okay? N equals a constant to infinity of our sequence a sub n, and it converges. Then that means that the limit of the sequence, right, the terms without the summation, the sequence is 0. I'm not going to prove it in longhand, but I want you to think about conceptually why this makes sense. I think it was Becca last time that said, wait a minute, how can we, well, you didn't say this, I'm putting words in your mouth a little bit, but this sort of counterintuitiveness of being able to add something together, infinitely many, things together, and then it actually stops at some value. And that seems kind of, not intuitive, right? That we should be able to do that. Well, let's just think. If the limit wasn't 0, right? If the limit wasn't 0, the limit's 1, right? All the numbers in the sequence eventually approach 1. It has an asymptote, a horizontal asymptote at 1. And you're calculating area under curves, or you're calculating the summation of multiple things added together. Well, if I keep adding something that's 1 to it over and over again, it's never going to actually approach a single value because it can always get one bigger. It's like having this conversation with your 4-year-old that says, I love you to infinity, and they say, I love you to infinity times 2. And you're like, okay, right? It's still infinity, right? Like that's what you're doing there, right? Like I can't actually make it be not infinity if I keep adding 1 to it because it's always 1 bigger than it was, previous term. So the only way that a series is going to converge, the only way is going to necessarily have the limit of the sequence itself approaching 0. Okay, so I actually just said that sort of backwards because that's actually my next theorem. Theorem 9.9 is the contrapositive for this. So this is the nth term for divergence. And it says the following. If, in fact, the limit of your sequence is not 0, maybe it's 1, maybe it's infinity, maybe it bounces back and forth between -1 and +1 like with sine, okay, but it's just not 0. Then, whoops, your summation from n equal 1 to infinity of a sub n diverges. And I'll write this out because I said it. Hopefully it'll go in your mouth. These are contrapositives. What I want you to notice, though, is what it does not say. And I'll explain why when we get to 9.3. But you need to know this does not say that if you have the limit of the sequence in fact going to 0, that the series converges. Sometimes it does, and sometimes it doesn't. So just having the limit of the sequence approaching 0 or becoming 0 or equaling 0, I don't care what language you want me to use, but just having the limit 0 does not make the series converge. But if the series converges, then it would have had to have been true that that limit would have approached 0. Okay?
Is that like referencing because we basically call like an asymptote on a graph where it goes to -infinity right at 0?
No. I'm going to give you an example of one that fails so you can see where it fails. It's actually got a specific name. It's called the Harmonic Series, and we'll do that in 9.3. So I'm hoping to get there today. Let's do one last thing in this section so you can see this actually in play. An example. We're going to determine the convergence or divergence of the series. And we're going to take a look at k equals 1 to infinity of 3k over k plus 4. I kind of hope at this point you might be able to look at this and just tell me what you think the limit is without doing any algebra or simplifying. Any idea? It's 3. That plus 4 in the denominator is really not important. Doesn't affect the problem very much. So basically, we really have 3k over k, and that's 3. So this limit is 3. Let's actually show that. There's lots of ways you can show that. If you like L'Hopital's rule, more power to you, you can use it. If you like ratios, that's what I'm going to do. We can use that. So if I multiply by 1 over k, top and bottom, then this gives me the sum from k equal 1 to infinity of 3 over 1 plus 4 over k. The 4 over k part goes to 0, right? So this is equivalent. And I don't need the summation. I meant to do limits here. My bad. There we go. So as I'm looking at the limits, I end up with this becoming 3. So by the, how do we call it, nth term for divergence test, the limit of my sequence, which was 3k over k plus 4, as k goes to infinity, is equals to 3, which is not 0, obviously. So the summation from k equals 1 to infinity, I did it with 1 here, yeah, of 3k over k plus 4 diverges. Again, I'm going to say it one more time. The nth test for divergence cannot prove something converges. All it can do is prove something diverges. All it can do is prove something diverges. Okay, so everybody have what they need written down for the slide. Still working, Ethan?
Kind of. I got the gist of it, but.
Do you have a question?
So, this sorry, I'm just getting myself confused about convergence and divergence.
Mhm.
Divergence is when it goes to infinity, it doesn't have like a limit.
It could go to infinity. It also could be something that has an oscillating feature, like the sine graphs. If you were looking at like those values, they wouldn't converge either. They would diverge, but they wouldn't diverge to infinity necessarily. They could bounce up and down between positive and negative numbers for infinity, you know. It's kind of like talking about the fact that pi doesn't have an ending value, right? There's no repeating patterns, there's no nothing, it just keeps bouncing around, sort of what feels like kind of at random. So it could do that too and still diverge. Okay? All right.